Hello everyone, in this video I'm just going to give you the solutions to the question 2. So the final question in the tutorial 6, which is regarding the properties of water and steam. So let's have a look at this question. So first of all, we know the mass. Okay, we know the mass, which is 0.5 kilogram. So that's obviously in a closed system because the mass is fixed, of wet steam. Okay, so wet steam at a temperature, so we know that temperature undergoes an isobaric expansion. So isobaric means that it's a constant pressure. Okay, constant pressure process. Okay, so from the lecture slides we know that we learned the process of water when it is heated under a constant pressure. For example, it's at the atmospheric pressure, and then we get that curve. Okay, and that curve is exactly an isobaric curve. So the pressure is under 10 is equal to 10 bar. P is equal to 10 bar. Okay, and if the initial dryness fraction, that's because it's a wet vapor, so it has got a dry fraction here. It's 0.6. Okay, and this is a process. You see, it's a expansion process, and so all this information is regarding the initial point. Okay, and then we get the final temperature of that steam after expansion is 400. So this is something about the temperature after the expansion, so it's got a temperature of T2 here. Okay, so first of all I'm going to plot this process, okay, schematically on that TV diagram, so you can better understand what the process look like. So we can also identify what are the phases of the water, at the initial point and also at the end point. Okay, so first of all I'm going to plot a TV diagram. Okay, so the y-axis will be the temperature, right? So it's in centigrade, and this is the volume, specific volume, V, so in cubic meter per kilogram. Okay, so to plot any diagrams on this TV, any plots on this TV diagram, especially for the steam and the water system, in which there's a phase change involved, so we needed to plot a dome shape like that. So it's very useful for us to understand all the processes according to this dome shape, because this profile shows us, okay, anything here underneath this dome. Okay, so these are all the wet vapor. Okay, so any points on here represent a wet vapor. So anything on left hand side of here represent a liquid, and anything on this side represent a superheated vapor. Okay, so what we're going to do is to plot this process on this TV diagram, and because this is isobaric, which is a constant pressure process, and as you know that we actually learned this process something like that. Okay, so a steep increase, okay, to this point, so this represents a saturated water, and we then have a platform like that. Okay, so this is a evaporation process, and anything here represents a wet vapor, and above that, once we reached the saturated vapor line, okay, and then the curve goes up again. Okay, so we just call this curve a constant pressure line. Okay, in this particular case the pressure is equal to 10 bar. Okay, absolute isobaric pressure, which is 10 bar here. Okay, so this just means, okay, this is isobaric expansion process. And now we need to find out the initial point and the end point. Okay, initially this is a wet steam. Okay, it's a wet steam. So wet steam can only be this section here, okay, somewhere, and because we have a dryness fraction of 0.6 here, so it's maybe about here. So you don't actually need to plot the exact very accurate position, so we just need to give a rough position like that. So this is a point of 1, okay, because it's definitely a wet vapor. Here, 10 bar. So if you look at the steam table, we will find that at a pressure of 10 bar, the saturation temperature is exactly that, okay, 179.9. So this is here. So TS, right? So TS here is 179.9 degree. And let's have a look at the final state. So after expansion, the final temperature of the steam after expansion now is 400 now. So 400 is obviously much higher than that. Okay, so you have to go beyond that point so that the temperature can be increased. Otherwise, in this section, temperature will be just kept the same as 179.9. So 400 is somewhere here. Okay, so let's assume that this is 400. So this is our end point, which is 2. And the process is from 1 to 2. So I probably can put an arrow on it to show how the process look like. Okay, so that's a PV diagram, and on this diagram we have shown that the initial state, which is a wet vapor, and the final state, which is a superheated, okay, superheated vapor. So you need to understand the location of these two state numbers, and you need to understand the process. You will use all these understandings for the following calculations. Okay, now let's have a look at the first question, number 1. The initial volume of that steam. So we're talking about the volume, okay? So we need to find out any information about the specific volume of that steam now. Okay, so for the initially, we know the steam, we know the pressure, okay? So most importantly, we know the pressure, and because it's a wet vapor, so the volume, okay? So the volume of the initial state, because it's a wet vapor, right? It's a wet vapor. So we just write the equation for the wet vapor, which is x times Vg subtract 1 subtract x add 1 subtract x times Vf. So this is for the initial state. We obviously know the dryness fraction already, that's 0.6. And then we just need to find the Vg and the Vf at the pressure of 10 bar. Okay, so now we just use the steam table here. Okay, so first of all, we need to find out the Vg. So let me find out the pressure of 10 bar. Okay, for saturated water and steam, you can see the third column is Vg, right? So we just need to find the pressure, because pressure is 10 bar. So that's 10 bar, third column, okay? So that's 0.1944. So that's for Vg. So we have Vg at 10 bar is equal to 0.1944 cubic meter per kilogram. And also we need to find the Vf. Okay, as I said, you can't find the Vf here, so you need to get to the page 10. Okay, page 10. It's called the further properties of water and steam, according to the second column, pressure here. And then we find the 10 bar. Okay, so 10 bar is very, very close to 10.03 bar. So we can just use that value, which is 0.1128. And remember, into times 10 to the power of minus 2. So that's Vf at 10 bar. So we just use 10.03 bar, okay? And then we'll get the value is 0.1128 times 10 to the power of minus 2 cubic meter per kilogram. Right, so we have found the Vg, we have a Vf, and then we can use that equation. We can just use that equation to calculate the V1 is equal to V wet. Okay, so x is 0.6, should be given here, 0.6 times Vg first of all. at 1 subject S, so we have 0.4 times 10 to the power of -2. Okay, so after that we can calculate, this is about 0.1171 cubic meter per kilogram. So we need to have a look at the question actually. So this is called the initial volume of that steam. So it's not initial specific volume. So this means that that's a capital V. Okay, that's a total volume. So we need to calculate V M. We need to times the specific volume by the mass here. Okay, the mass is 0.5. Okay, 0.5 kilogram times, okay, which give us the 0.0585 cubic meter. So that's for the first question. Now what we are going to do is to calculate the second one, which is the work done by the steam. So how are we going to calculate the work done? So think about up to now, what equation have we learned? What equation have we learned regarding calculation of the work done? Okay, so that's the formula sheet. The work done here. Okay, we have a couple of equations, especially for the isobaric, because this process is actually the isobaric process. So we're going to use isobaric process, that equation. So the work done is equal to P times delta V. Okay. So the work done 1 to 2 is equal to P. So P1, P2 is the same. It's the same as 10 bar. Okay. Times V2 and the state. Okay. And the state, subject, initial state. Be careful, these are all the capital letters. So these are the total volume. Okay. And then we have used a lot, by using the specific values. So I'm just going to write this P times M, lowercase v2, subject lowercase v1. Okay. So v1 actually we already calculate that. v1 is v wet, already calculate that. And then we need to find out is the v2. So let's think about v2. v2 is end state. So our end state is here. To find any properties on here, which is a saturated vapor, I just explained this earlier. Okay, so this represents a superheated, it's a superheated vapor. Okay, so we need to find out the specific volume of a superheated vapor at a pressure of 10 bar and also at a temperature of 400 degrees. So now we're going to use steam table again, but this time we're going to use the section for the superheated. Okay, because it's superheated steam now. Also we need to find out the pressure, which is 10 bar. So here you can see I'm using superheated steam. Okay, superheated steam, and on the 10 bar is here, so we're using this 9. Okay, and also we need to find the proper temperature, which is 400. So 400 is here. Okay, and then we're looking at V. So the first value is a V, so it's a 0.3065 cubic meter per second. Sorry, cubic meter per kilogram. So now we already found out that V2, okay, V2 is superheated vapor, and from steam table we found V2 is 0.3065 cubic meter per kilogram. Right, and then we just check the equation again. So pressure, we know that pressure, we know the mass, we know V2, we know V1. So everything has been given, and then we'll be able to calculate the work done. So the work done from 1 to 2 is equal to pressure. Okay, be careful, now we're going to convert everything into SI base unit. So pressure is 10 bar, okay, So 10 bar, 10 times 10 to the power of 5, so that's Pascal, times Vm is 0.5 times V2, yeah, except V1. Okay, then you'll be able to calculate the values Joule, okay, because we're using SI base unit all through, and the final answer must be SI unit as well. So if you think this is a little bit too big value, then we can just convert that to kilojoule. So it's 94.7 kilojoule. Okay, so that's for the second one. Right, let's have a look at the third one. So the third one, we need to calculate amount of heat transfer. Okay, so if you have practiced a lot on the first topic, you know, that's closed system, and you know, we have different thermodynamic processes, and how are we going to calculate heat transfer is based on the first law of thermodynamics. So here, so there's a formula sheet. Okay, so you can see the first law of thermodynamics in closed system. So we have this equation, right? This equation, because this equation has established, you know, the relationship between heat transfer, work transfer, and also the change in the internal energy. Okay, so now what I'm going to do is just write that equation down first of all. Okay, so I'm going to write the first law of thermodynamics, Q subset of 1, Q subset W is equal to U2 subset U1. Okay, so this is basically the first law of thermodynamics for any closed system, for any process. Again, this is capital, so I'm going to write in lowercase. This is because on the steam table, all the values is found. They are actually all in the specific forms. Okay, U2 and U1. So what we are going to calculate is the amount of heat transfer during this process, heat transfer. So we are going to calculate heat transfer here. So think about W1 to 2. We just calculate W1 to 2. Okay, and then we know the mass, right? So what we need to calculate is actually we need to find out U2 and the U1. Okay, so now we have a look at the U1 first of all. U1. So where's 1? 1 is a wet vapor. Okay, so U1, because this is a wet vapor, is just equal to U wet. And how to calculate U wet? We have the similar formula, right? Similar formula as that. So it's just equal to X times UG at UF. Okay, and the UF and the UG can be found because this is at 10 bar, right? 10 bar. So according to that steam table, we're going to check again to find the UG and the UF at the pressure of 10 bar. So let's saturate the water in the steam. 10 bar is here. Okay, 10 bar is here. And the UG and the UF. So that's UG and the UF, right? So it's 10 bar is here. Okay. So that's UF 762 UF, and the UG is 2584. So then we just write them down. UF is 762, UG is 25884, and then we know the X, right? And then we'll be able to calculate the U1 X, the same, so that's 0.6 times UG 2584 at 1 subject X gives us 0.4 times UF 762, which is equal to, okay, equal to 1,805.5.2 kilojoule per kilogram. So that's U1. And also we need to find out U2. So we need to always check the phase first of all, so that we know, in the steam table which section are we going to use. Because 1 is a steam table, so it's wet vapor, so we're using that equation to find out 1, right? However, for 2 is superheated. Okay, so we need to use a superheated section to find out the U values for section 2, using the pressure, using the temperature. Okay, so now again we need to, so this time we can't use a saturated water and steam now, so we need to find out the superheated steam. Okay, so that's superheated steam. And then we need to find out the pressure, 10 bar, okay, 10 bar, and also the temperature, 400, okay, 400, 10 bar, so that's a group of data over here. Okay, so the first one have already used that for V, that's for V, okay, that's for V, and the second is for U. Okay, so be careful, that's 10 bar, 400, second one U, so that's 2957, right? 2957. So we have already just found the 2957 for U2. Okay, kilojoule per kilogram. Now it's possible to calculate the Q12 because we know all these values. Okay, so I'm just going to move W12 to the right hand side. So this will give me 2Q. Okay, 122 is equal to W122, which have been given there, have been calculated 94.7, add the mass, which is 0.5 times U2 is here, 2957. Subtract U1 19445.2. Okay, then we'll be able to calculate. The final answer is 645.6 kilojoule. Okay, so this question looks like a little bit complicated. Okay, so this is because we do need, understand how to find out all the properties of the water and steam depending on what status they are. So we need to decide first of all if this is a wet vapor or if it is a superheated vapor, and then we use different sections in the steam table to find out all the information about about the specific volume, about the internal energy. Okay, so it all depends on what kind of equations are we going to use, right? So if we use this equation to calculate the work, then we need information regarding specific volume. If we need this equation to calculate the heat transfer, then we need information about the internal energy, and all these you need to find out all these from the steam table. Okay, so that's the solution for question 2 in tutorial 6.